Hello everyone, now we will have a tutorial class, and in this class we will discuss on some problems related to the discussion we have made in the last 4 classes. First problem, the statement is calculate the plate area of an electrostatic precipitator removing 90% of particulate matter from the exit gas of a cement industry having 200 ppm of particulate matter. What change in plate area of above mentioned ESP would be required to improve the collection efficiency from 90% to 99%. Assume the exit gas flow rate as 150 meter cube per second and the drift velocity of particles W is equal to 0.11. So, this is the problem of electrostatic precipitator. Already we have made discussion on it in our previous classes, and here we see that collection efficiency for ESP can be determined by this expression 1 minus e to the power minus W A by cube. So, in this case W is drift velocity. So, here 0.11 and A is the surface area of the collector of this ESP and Q is the volumetric flow rate. So, it is given that 150 meter cube per second. So, Q value is given and W value is given. So, in this expression efficiency is also given, that is equal to 90%. So, 0.9 we will put it here. So, 1 minus e to the power minus 0.11 A by 150. So, from these expressions if we calculate, we will get the value of A, the first case A 1, we are assuming A 1 for the first case, that is equal to we are getting 3139.89 meter square. So, this is the area which is required to get 90% efficiency for these applications using the ESP. Now, if the efficiency we need to increase from 90 to 99%. So, then the final efficiency will be 0.99, that is equal to 1 minus e to the power minus 0.11 A by 150. So, here we will be getting the value of A, that will be A 2. So, corresponding A 2 we will be getting by solving this expression, that is 6279.77 meter square. So, this is the area required for the second case, that is for 99% efficiency, and this is the area required for the first case, that is for 90% efficiency. So, increase in plate area is A 2 minus A 1. So, that is equal to 6279.77 meter square minus 3139.89 meter square, that is equal to 3139.88 meter square. So, the problem is solved. Next we will see problem number 2. The statement is an ESP is to be constructed to remove fly ash particles from stack gases flowing at a flow rate of 10 meter cube per second. Analysis of a similar system shows that drift velocity can be taken as W 3 into 10 to the minus 1 into dP, and the dP is the particle diameter in micrometer and W is in meter per second. So, determine the plate area required to collect particulate matter of 0.5 micrometer size with 99% efficiency. So, we have to calculate the area requirement again. In this case the efficiency is 99% for the particle size of 0.5 micrometer, and the drift velocity here it is given as a function of dP, that is the particle diameter. So, in our case dP value is 0.5 micrometer. So, we will be calculating that W is equal to 3 into 10 to the minus 1 into 0.5, that is equal to 0.15 meter per second. So, this is our drift velocity. So, this W value we will use in our efficiency expression, that is efficiency of ESP is equal to eta is equal to 1 minus e to the power minus W A by Q. So, what will be the W then? We will be taking both sides ln. So, ln 1 minus n that is we will bring this 1 to this side. So, 1 minus eta or minus 1 minus eta minus 1. So, this is equal to ln 1 minus eta. So, that is equal to we are getting that is minus. So, we can take this one also here by this expression we are taking this e to the power minus w a by q and negative side taking this side. So, e to the power minus w a q and this side is 1 minus eta, then we will take ln. So, ln 1 minus eta is equal to we are getting minus w a by cube, or we can get w is equal to minus q a into ln 1 minus eta. So, these expressions which we have written here. Now, in this case w is given that is equal to 0.15 meter per second we have calculated. So, we will put it here w value, and then q is also given 10 meter cube per second. So, minus 10 divided by a into ln 1 minus efficiency is 99%. So, 0.99. By solving these expressions we are getting a is equal to 307.011 meter square. So, this is the area of the collector which is required to get 99% efficiency for the separation of the particle having 0.5 micrometer size. So, now we are able to solve the problem. Next we will have problem number 3. The statement is calculate the sedimentation rate in gravity separation for the particle size limiting to d limiting that is equal to 7 micrometer, the particle density 1040 kg per meter cube and liquid density 1000 kg per meter cube and viscosity of continuous phase equal to 1 into 10 to the minus 3 Newton second per meter square. So, this is the problem related to gravity separation. So, in case of gravity separation, if we assume that laminar flow regime is applicable, then laminar gravitational free settling velocity will be dp square into rho s minus rho l into g by 18 mu, that we know. So, in this case what we are having that is equal to dp square. So, dp is given 7 micrometer. So, 7 into 10 to the minus 6 converted to meter 2 square dp square into rho s minus rho l. So, 1040 minus 1000. So, that means we are getting this one. So, divided by 18 into mu is equal to 10 to the minus 3. So, 0.001 and g is equal to 9.81 MK system. So, we are getting that the laminar gravitational free settling velocity is this expression. So, by solving this we are getting 1.068 into 10 to the minus 6 meter per second. So, then problem number 4, the statement is a multi-tray settling chamber having 8 trays including the bottom surface handles 6 meter cube per second of air at 20 degree centigrade. The trays are spaced 0.25 meter apart and the chamber is to be 1 meter wide and 4 meter long. What is the minimum particle size of density 2000 kg per meter cube that can be collected with 100% efficiency? What will be the efficiency of the settling chamber if 50 micrometer particles are to be removed? Then laminar flow condition within the chamber and presence of no dust initially on the trays may be assumed. So, this is given, and dp minimum we can calculate by using 18 mu gq by n wl g rho p minus rho g. In the above example, is the laminar assumption justified? We have to check it, and then if not, what is the collection efficiency for 56 and 50 micrometer particles. So, this which we have written here dp minimum, that is for laminar flow regime, and if we want to get the solution, so we will get the value of dp minimum. So, we will be using this expression, and this expressions we need to get the values of all these parameters which is given in the statement. So, now we will say the q. So, mu g at 20 degree centigrade, it is given 1.81 into 10 to the minus 5 kg per meter second, it is already given. Okay, this is the viscosity of water, and rho p is 2000 kg per meter cube, it is given. Now, since rho p is much greater than the rho g, so rho g may be neglected in the above equations, and substituting for n is equal to 8, it is given n equal to 8 and w equal to 1 meter and L is equal to 4 meter as per the statement, and g is equal to 9.81 meter per second square, that is equal to small g. Okay. So, we have dP minimum equal to 18 into 1.81 into 10 to the minus 5 mu g into then q is equal to 6 meter cube per second. So, this is one, and from the denominator we are having n, that is equal to 8 and w is 1 meter, L equal to 4. So, 1 into 4 into 9.81 g, and this as rho g is much less than the rho p. So, this can be neglected. So, we will be getting the 2000, and then dP minimum we are getting 56 micrometer. So, by solving these expressions we are getting dP minimum is equal to 56 micrometer. So, this minimum diameter is 56 micrometer when the flow is in laminar regime. Now, efficiency for dP, this is equal to for any other particle size. If we get any other particle size and want to calculate the efficiency of other particle size, so in that case it is proportional to dP square. So, that is dP is equal to efficiency of any particle size, that is equal to dP by dP minimum square. So, efficiency of dP for 50 micrometer particles. So, what will be dP 50 by 56 square. So, that is equal to 80%. So, this is the first part. First part we had to calculate what will be the efficiency of the settling chamber if 50 micrometer particles are to be removed, and then laminar conditions within the chamber are present and no dust initially on the tray may be assumed. So, on the basis of that assumptions we can get the for 50 micrometer particles, because this is our 56 is the minimum diameter. So, this minimum diameter particle size means we will be getting 100% removal. Now, the diameter is less than this 56 micrometer, that is 50 micrometer. So, efficiency is 50 by 56 square. So, that is equal to 50 by 56 square into 100. So, 80% we are getting. Now, second part we have to calculate, so is the flow is in laminar regime or not. So, for 56 micrometer particle and for 50 micrometer particle we will be calculating the Reynolds number, particle Reynolds number. So, REP, so here in this case rho dV by mu. So, rho is 2000 and d 56 into 10 to the minus 6 and then 6, that is volumetric flow rate divided by cross sectional area, that is equal to V. So, 6 divided by 4 into 1 and then by mu. So, 1.81 into 10 to the minus 5. So, this is mu. So, that we are getting 9281. So, particle Reynolds number. So, very high particle Reynolds number we are getting. So, this is not in the laminar flow. So, for the same case for 50 micrometer we are getting this 2000 into 50, this is 50 into 10 to the minus 6 into 6 by 4 into 1 into 1.81 into 10 to the minus 5. So, that is equal to 8287. So, here also the particle Reynolds number 8287 is very higher. So, in this case the laminar assumptions which we have considered are not correct, okay, for both the cases, and efficiency turbulence will be different from the efficiency which we have got in the previous slide. So, that efficiency in case of turbulent flow, that will be 1 minus exponential minus efficiency at laminar flow. So, we will be putting these values for the first case when we are having 56 micrometer particle size, then we have 100% efficiency. So, 1 eta turbulence equal to 1 minus exponential minus 1. So, that is equal to 63%, but in the second case for 50 micrometer particle efficiency was 80%. So, we will be getting for efficiency under turbulence, that is equal to 1 minus exponential minus 0.8. So, here we are getting 55%. So, actual efficiency will be 55% for 50 micrometer particle, and this for 56 this will be 63%. Now, we are able to solve the problem. Now, problem number 5, the statement is calculate the net air to cloth ratio for a reverse air bag house with 10 compartments containing 276 bags each. The diameter of each bag is 11 inch and the bag height is 28 feet. One of the compartments is always offline for cleaning and another is offline for maintenance. Use a gas flow rate of 3,50,000 ACFM. ACFM is actual cubic feet per minute. So, this is the statement. So, this is a problem of bag filter. So, in this case we have to calculate the area. So, individual area of bag, that is 2 pi r l. So, 2 pi r h, so or pi d h. So, here d is the diameter of it and h is the height of it. So, in this case pi into 11 inch, so 11 by 12. So, this is converted into feet and 20 feet is height. So, pi d h. So, this is 80.6 feet square per bag. So, this is the individual area of bag. So, now total bag area, we have individual bag area into number of bags per compartment into number of compartments. So, we have 10 compartments and per compartment we have 276 bags and one bag is having 80.6 feet square. So, this is the total area of the bags, that is 2,22,456 feet square. Then net air to cloth ratio, that is equal to Q divided by A. So, Q is equal to 35000 feet cube per minute, that is actual cubic feet per minute, divided by A, that is 222456, that is feet square. So, this we are getting 1.57 feet per minute. Next, problem number 6. Statement is estimate the liquid purge rate for a scrubber system treating a gas stream of 25,000 SCFM with a particulate matter loading of 1 grains per SCF. Assume that the scrubber particulate matter removal efficiency is 97% and the maximum suspended solids level described in the scrubber is 3% by weight, and it is given 1 pound is equal to 7,000 grain and SCFM is standard cubic feet per minute. So, we can solve like this, say calculating the inlet particulate mass. So, inlet mass is equal to, we can get 25,000 meter cube per minute, that is volumetric flow rate, okay, and 7,000 grain is equal to 1 lb and we have 1 grains per feet cube. So, this is equal to 2500 particulate matter loading this 1.0 grains per cubic feet. So, this is our SCF and multiplied by this 1 grains per feet cube. So, this equal to 1, this will be our grains and 7,000 grains is equal to 1 pound. So, divided by 7,000, that will be 3.57 pound per minute. So, this is the inlet mass and then collected mass is equal to efficiency into inlet mass. So, efficiency is 97%. So, we are getting 97 into 3.57. So, that is divided by 100. So, that is equal to 3.46 pound per minute. So, this is our collected mass and purged solids of 3.46 pound per minute are 3% of the total purge stream. It is given that this is suspended solids level desirable in the scrubber is 3%. So, that is the purge solids of this 3.46 pound per minute which you are getting, that are 3% of the total purge stream. Therefore, the purge stream is equal to 3.46 divided by 0.03, that is equal to 115.3 pound per minute, and a stream with 3% suspended solids has a specific gravity of about 1.03. Therefore, the purge stream density is equal to 8.34 pound water per gallon into 1.03, because we know that 1 gallon, this is equal to conversion, that is 8.34 pound and this is our specific gravity. So, 1.03. So, then we will be getting 8.59 pound per gallon. So, we are having per stream flow rate, that is equal to this we are having pound, and now we are having this pound per gallon. So, this will be 13.4 gallon per minute. So, now we are able to solve the problem. Next, problem number 7 statement is, a venturi scrubber is to be used to collect particulate matter from a gas stream. The liquid flow rate through the scrubber is 20 gallon per minute per 100 cubic feet per minute of gas, and the relative velocity of the gas to liquid is 400 feet per second. The gas is air at STP and carries particles of density 1500 kg per meter cube. Determine the efficiency of the scrubber as a function of particle diameter. Consider the viscosity of the gas as 1.8 into 10 to the minus 5 kg per meter second, and empirical factor for throat geometry and other parameters k is 0.2. So, this is a problem of venturi scrubber, and for this case we know that collection efficiency of scrubber is equal to 1 minus exponential minus k L into root of psi, when psi is equal to the impaction parameters, and this is the expressions of psi equal to C into rho p into dp square into Vr divided by 18 mu do, when do is the droplet size. So, droplet size can be determined by some expressions as given here, that is equal to 16,400 by Vr plus 1.45 L to the power 1.5, when L is nothing but the liquid flow rate, and that V is the relative velocity in the duct. So, droplet diameter is a function of liquid flow rate and gas velocity as this one, that you know, and in this case do in micrometer, and this formula we will put. So, in this case our getting this Vr is equal to 400, it is given 400 feet per second. So, this divided by 400 plus 1.45 into L to the power 1.5. So, what is L? L is equal to liquid flow rate. So, that is 20 gallon per minute per 100 cubic feet. So, this unit we should have L should be in this unit. So, L is equal to 20 to the power 1.5. So, that is equal to 170.7 micrometer. So, this is equal to 171 into 10 to the minus 6 meter. Then we are getting that Vr is equal to 400 feet per second, that is equal to 122 meter per second, because 1 feet per second equal to this 0.3048 meter per second. So, impaction factor now we will be getting psi. So, that is equal to C into rho p, that is equal to 1500, and dp square into 122, that we are getting Vr, and divided by 18 into 1.8 into 10 to the minus 5 into do. So, do value we are getting 171 into the minus 6. So, that way we are getting the value of 3.3 into C into dp square. So, this is impaction factor. So, we will put these values in the efficiency expression. So, 1 minus exponential minus k value is given 0.2 into L value is 20 and root of psi. So, root of psi value is equal to, this is our impaction parameter. So, root of this. So, 3.3 C into dp square to the power half. So, now we are getting that dp is coming out, and this root of C and root of 3.3 and then exponential minus 7.27 C to the power half into dp. So, this is the expressions it was asked to calculate, and now we are able to solve the problem. Problem number 8, a packed filter having 1.0 meter per second of standard air is packed with fibers of size 100 micrometer in diameter. Dust laden air passes through the filter with a velocity of 1.5 meter per second and the packaging density of 0.1. The average diameter of the particle in the air is 1 micrometer and the individual fiber efficiency is equal to 0.6. So, determine the dimensions of the packed filter if the overall efficiency is 99.5%, assume W equal to 8, and what is the filter length if eta is equal to 99.9%. So, this is a problem of bag filter, and we know that face area of the filter, that is equal to AF, that is volumetric flow rate, divided by V into 1 minus F. So, 1 minus F means this is equal to 1 minus F means F r is the fractions of the fabric. So, 1 minus F f is equal to the fractions of the cross sectional area if we multiply A f into 1 minus F f. So, that will be the cross sectional area free, not occupied by the fibers. So, through which the air will pass. So, multiply it by velocity. So, then that will be the volumetric flow rate. So, that is equal to 1 divided by 1.5, it is given, because this 1.5 is given meter per second, this is the velocity. So, that velocity into 1 minus 0.1. So, 0.74 meter square, we are getting that the face area of the filter. The length of the filter L is equal to again pi d f 1 minus f f L n 1 minus eta f 4 f f. So, this formula. So, we will be putting this value L is equal to pi into d f 100 into 10 to the minus 6. So, 100 micron. So, this will be 10 to the minus 6 meter. So, 1 minus 0.1 and pi f 4 into 0.1 and this value is equal to 0.6 and ln 1 minus 0.995 for 99.5% efficiency it is given. So, we are getting L equal to 0.006236 from this expressions by solving the value of L, and the filter length L, if it equal to 99.9%, then what will be the same expressions will be using and replacing this value 0.9999. So, L value will be this one 0.01084 meter. So, now we are able to solve, and problem number 9, the statement is what is the aspect ratio for a 5 field electrostatic precipitator having collection plate heights of 30 feet, collection plate lengths of 9 feet and a precipitator with normal to gas flow of 50 feet. So, this is a problem of again ESP. So, here aspect ratio you know that L by H. So, height is here as 30 feet and we have 5 fields and each field we have 9 feet length. So, 5 into 9 divided by 30 or 1.5 will be our aspect ratio. So, the aspect ratio for a 5 field electrostatic precipitator is 1.5. So, now the problem is solved. So, up to this in this class, thank you very much for your patience.